to second order circuits, which are composed of a resistor, an inductor, and a capacitor, or RLC circuits. So first, let's talk about the natural response of a parallel RLC circuit. So applying KCL at the top node, KCL at top node, we have IC plus IL plus IR equivalent to 0. Now take note that R, L, and C are in parallel, so the voltage across them are just equal. And we should take note that the voltage in an inductor is given by V equals to L DIL over dt. Or in terms of V, our IL equivalent to 1 over L integral of v dt plus the initial value of I. So in terms of IL, the current in the capacitor can be expressed as C dV over dt plus IL plus V over R equal to 0. Now take note that our V is equivalent to L DIL over dt. So this term becomes L times C, second derivative of I L over dt plus IL plus L over R DIL over dt equal to 0. So if we rearrange this equation, we have d squared IL over dt squared plus 1 over RC DIL over dt plus 1 over LC IL equal to 0. Or in terms of V, our equation becomes, we have C dV over dt plus, so IL in terms of V, just this equation, we have 1 over L integral of v dt plus IO plus V over R equal to 0. Now deriving this equation on both sides, we have T and derivative of V with respect to time plus 1 over L V, derivative of a constant is 0. We have plus 1 over R derivative of V with respect to time. Now rearranging this equation to become dV squared over dt squared plus 1 over RC dV over dt plus 1 over LC d equal to 0. We have our equation in terms of I, our equation in terms of V. So notice that the coefficients are the same. We have 1 over RC, 1 over LC, then we have 1 over RC, then 1 over LC. This shows that the solution for IL and V are just of the same form. So let's take a look at IL. So assuming a solution of IL equal to AE to the ST, or if we take a look at V is just the same form as IL, so BE to the ST. Looking at L, we have taking the second derivative of this equation, this solution, plugging it into this equation right here, we have second derivative is equivalent to A S squared E to the ST plus we have 1 over RC, and we have A SE to the ST, and plus 1 over LC E to the ST equal to 0. Now take note that we are using this equation and this. Factoring out the A E to the ST, this equation becomes S squared plus 1 over RC S plus 1 over LC equal to 0. For this equation to be true, for this solution to be true, this right here should be equal to 0. So we have S squared plus 1 over RC S plus 1 over LC equal to 0. For finding the roots, we have two values for S. So we have S1 and S2 just equivalent to negative 1 over 2RC plus minus square root of 1 over 2RC squared minus 1 over LC. We introduce new variables. We have alpha is equivalent to 1 over 2RC, which is called the upper frequency. Then we have omega naught, which is called the, which is equivalent to 1 over square root of LC, which is called the resonant frequency. So now our S becomes, we have negative alpha plus minus square root of alpha squared minus omega naught squared. We have solution for IL of t into A1 e to the S1 t plus A2 e to the S2t. Or in terms of voltage, we have V1 e S1 t plus V2 e the S2 t. Now these solutions only true if alpha is greater than omega naught. In this case, the circuit is overdamped. Now S1 and S2 are called the characteristic roots. Alpha is the Neper frequency and omega naught is the resonant frequency. For a parallel RLC circuit, S1 and S2 are given by these equations, where alpha is given by 1 over 2RC and omega naught is 1 over square root of LC. Three possible scenarios depending on whether alpha or omega naught is larger or they are equal to each other. So we have overdamp, alpha is greater than omega naught. We have critically damped where alpha is equal to omega naught, and then the underdamped where alpha is less than omega naught. Now since we have the solution for the overdamped circuit, let's take a look at the critically damped circuit. So critically damped, meaning our alpha is equivalent to omega naught. So this means that our S1 is just equivalent to S2, or which is just equivalent to negative R over 2L. So in this case, our IL of t is equal to A1 e to the negative alpha t plus A2 e to the negative alpha t, or you can combine this, you can factor out e to the negative alpha t. We have A3 times e to the negative alpha t. Here A3 is equivalent to A1 plus A2. So is this really true? So this equation cannot be our solution, because there are two initial conditions. So what are the initial conditions? So we have initial value of I, and then we have the initial value of V. So these two initial conditions cannot be satisfied with only one constant, K3. Looking at the equation, we only have one constant. So our equation, so this, the proper derivation for this solution is discussed in engineering mathematics. In this case, multiply our first term with t. So our solution becomes A1 t e to the negative alpha t plus A2 e to the negative alpha t. Voltage is also with the same form. Now, if we take a look at the underdamped case, underdamped, we have alpha is less than omega naught. So we have the value of our S1 and S2 will become complex numbers. We have negative omega naught squared minus alpha squared, or it's just equivalent to negative alpha plus minus j omega d. You all know j is just of negative 1, and then for wd is just square root of omega squared, omega naught squared minus alpha squared. Our IL of t is equal to A1 e to the negative alpha minus jwd t plus A2 e to the negative alpha plus jwd. We have t. Now using Euler's identity, so Euler's identity, we have e to the j theta is equivalent to, for our j to the negative, now e to the negative j theta equal to, factoring out e to the negative alpha t, we have ae or jwd t plus a2 e to the negative jwd t. So using Euler's identity, the equation becomes, combining like terms, we have e to the negative alpha t a1 plus a2 cosine of wd t plus j a1 minus a2 sine wdt. So if we let this coefficient be 1, and then this is b2, our final solution for it is e to the negative alpha t quantity b1 cosine wdt plus b2 sine wd